Hello and welcome. My name is Alexander Moreira with AlphaStar Academy, and today we're going to be discussing the problem printing sequences from the 2025 February USACO Bronze Contest. In this problem, we are given a sequence of the numbers from 1 to k, and our goal is to determine if Bessie can print the sequence using a program that only consists of loops and at most k print statements. Here, k is a small number. In particular, it's between 1 and 3, and the length of our sequence n is between 1 and 100. So let's take a look at an example here, and we're going to start with a pretty long sequence, just so we can sort of get a sense of the flavor of this question. So what you'll notice is this sequence has a lot of repeating patterns. So it goes 4 2s, then 2 3s, and then this section repeats, and then this entire section repeats a second time. So we want to see if we can sort of create a program that will produce this output when we run it. And since k is 3 here, we are only allowed 3 print statements in our program. So let's take a look at such a program. So you can see that we've got 3 print statements here. So we've got print, print, and print. And the rep here stands for repeat. So this is just their syntax version of a for loop. So this is repeat the code 2 times, repeat the code 2 times, repeat the code 4 times, and so on. So I claim that this program will generate this sequence. So let's start here in the nested loop where we can see we're going to print the value 2 4 times. So that would give us the sequence 2 2 2. And after this loop ends, we will then print the value 3 2 times. So that adds 3 3 3. And we can see that this entire block of code gets repeated 2 times. So this sequence gets printed twice in a row. And right before we print out this sequence, sorry, this should be an end here. Right before we print out this sequence, we print a 1. So we print 1, and then we go inside this loop where we print out 4 2s, then 2 3s, and we repeat that sequence twice. And then the outermost loop here repeats this entire thing one more time to get this long sequence, and we can see that it precisely matches the sequence given in the example. So in this case, our output would be the word yes, because it was possible to construct this program that produces this sequence. If we had a sequence with less repetition in it, something sort of, let's say, that looked like this, something wild, something without a whole lot of repetition in its structure, then we would print out no. It is impossible to produce this sequence with exactly 3 print statements. So there's a lot of different ways you could approach this problem. You could either try to take a sequence and then apply some sort of clever process to that sequence to try to construct a program. Or alternatively, you could try to brute force over all programs and see if any program produces the desired sequence. So let's analyze the case k equals 2. So we're only given 2 print statements, and each sequence consists of the numbers 1 and 2 to see if maybe the brute force approach is feasible. To make progress in this problem, we want to make a key observation about the types of programs that are possible when k is equal to 2. And the key insight here is there are actually not that many programs that are possible when we only have 2 print statements. In particular, all programs have to have the following form: x, a loop over some value x, and then inside that loop, we can have a loop over y with a print statement and a loop over z with a print statement. And these print statements could be sort of printing out 1 or 2, 1 or 2. We're going to ignore that detail for now. But the primary choices here is we have a choice for the value of x, a choice for the value of y, and a choice for the value of z. And on the surface, that seems concerning. So if we have to sort of loop over all values for x, all values for y, all values of z, that could add up quickly if I had to loop x from 1 to n, loop y from 1 to n, loop z from 1 to n. Already you have an n cubed algorithm, and then you're going to have extra factors for looping over the test cases, extra factors for checking equality between the sequences. So you're going to end up with a very slow program here. But the good news is these variables do not exist in isolation. We know that the length of the sequence is going to be precisely n, and these variables will give us the length of the sequence. In particular, if I have the length of this subsequence, which is just y plus z, y plus z times x, the number of times this subsequence gets repeated, must be equal to the length of the total sequence. And this gives us several constraints on these variables. First off, we know that x has to satisfy the equation n mod x is equal to 0. In particular, this is just saying that x must be a factor of n. So instead of looping over all of the possible values for x between 1 and n, we only have to loop over the factors of n. And then, because we know that y plus z is equal to n divided by x, we know that z can be expressed as n over x minus y. So if we know y, we don't have to loop over z at all. And z is just immediately given to us in terms of x and y. So really the only variable that we have to have a large loop over is y, and we should loop over the values from 0 to n over x. This is the maximum possible value of y. So x will loop over the factors of n, y will loop over the values from 0 to n over x, and then for z, we'll just compute it using math. And what you'll notice here is we actually don't end up with with too many loops. Numbers don't have a whole lot of factors, and y only is looping over n divided by x. So as x grows, y will be looping over a smaller and smaller range of values. So this gives us some confidence that for at least the k equals 2 case, we can just simply brute force over all programs. So let's jump into the code here and take a look at what that would look like for the k equals 2 case. And then we'll continue on to the k equals 3 case. So the first thing we're going to do is, of course, read in all of the input data we need. So in these programs where you're tasked with sort of printing out some solution over multiple independent test cases, I like writing a function called solve, where I just loop t times and print out the value of solve. And then inside my solve function, I'm going to read in the data for that particular test case. So here I'm going to read in n and k, and then the sequence a. And the first thing we want to do here is note that we can sort of ignore the case k equals 1. It's not a very interesting case. You can analyze it on your own, and the answer is always going to be return yes. So for k equals 1, the sequence is always possible to construct. You just print out however many ones you need to, and life is good. For k equals 2, we want to first make our choice of x. So we're going to loop over all of the values from 1 to n, but remember our crucial observation that we only care about a choice of x if it is divisible or if it divides n. So if x does not divide n, then we're going to just continue on to the next value of x. However, if it does divide n, then we're going to loop over all the possible choices of y from 0 to the value n over x. And then Using this math formula, we can compute our value for z. And now we want to generate our sequence. So what is our sequence going to look like? Well, it's going to look like y copies of whatever this question mark is. So let's arbitrarily say this is a 1. Let's arbitrarily say this is a 2. So it's going to be y copies of 1 plus z copies of 2. And then we are going to repeat that x times. So we can take sort of this array and just append it to itself x times. So if this array is equal to the original sequence, we should return yes. And that's exactly what this line of code is doing here. It's computing the sequence where we print out 1 y times, 2 z times, and then we repeat that x times. If that's equal to the original sequence, we return yes. Otherwise, the other case is if I print out 2 first and then 1 second, we can check that by just doing 2 times y and then 1 times z multiplied by x. If that's equal to a, then we return yes. And this brute forces over all possible programs for the k equals 2 case. And the question is, can we do the same for the k equals 3 case? So let's go back to our notes here and see if we can make a similar key observation for the k equals 3 case. For k equals 3, the situation is similar, but slightly more complex. When k equals 3, there are actually two sort of possible programs. And they're the same as the programs for the k equals 2 case, but we've just replaced one of the inner loops with another nested loop. So here we used to have a loop over y with a print statement, but now we have a loop over a, and inside that we have another nested loop over b and c. The only difference between the left program and the right program is that in the right program, we replace the loop over z with the nested loop instead of the loop over y. Now, these two programs are actually symmetric under the reversal of the sequence. So if we just solve the problem for this program type, if we reverse the sequence A, we can also check this program type at the same time. So we can sort of ignore this case, although it would be fine to write out a separate chain of logic for this case as well. You just be worried about sort of runtime, particularly in the slower languages like Python. So the situation is a little bit more complex here. So what choices do we have in this program? We have a choice for X, just as before, a choice for Y, a choice for Z, a choice now for the values A, B, and C. So, but we've got a couple extra math formulas. So we have this original formula, X times Y plus Z is equal to N. And now we're replacing the loop over y with this nested loop over a, b, and c. So we get the additional formula that y must be equal to b plus c times a, right? So the number of total print statements contained in this section has to be equal to that original value y. So that gives us a new formula, a times b plus c plus z times x must equal n. So this gives us actually a lot of constraints on these variables. We get the same constraints from before, right? So x still has to be a factor of n. Y still has to loop over the values from 0 to n divided by x. Z we can still find using a math formula. But now, for these new variables, we can use this equation to do the same reduction here. So we can see from this formula that a has to be a factor of y. So when we're looping over the values of a, we actually only need to loop over the factors of y. When we're looping over b, we just need to loop from b equals 0 up to its maximum value of y divided by a. And similarly, we get c is at most, or c is rather exactly equal to y divided by a minus b. So where is this coming from? It's coming from the exact same transformation we did with the other formula. We take y, divide both sides by a, and we get y divided by a is equal to b plus c. So if we solve for c, we end up with c is equal to y divided by a minus b. So b can be anything between 0 and y divided by a, and then we solve for c. So what you'll notice here is we have the two original loops over x and y, and now we have two new loops. But the nice thing here is that they're very small loops, right? Looping over the factors of y is a very fast loop, and then looping over the values from 0 to a, from 0 to y divided by a is also small because as a gets bigger, y divided by a gets smaller. So even though we've added two new loops to our program here, we can still be optimistic, especially given the small size of n here, that we should be able to brute force over all possible sequences or all possible programs. The one thing that's tricky in this k equals 3 case is the fact that unlike before, there's now a lot of different possibilities for the different sort of arrangements of the print statements, right? So that could print out a 1, 2, or a 3. This one could print out a 1, 2, or a 3, and this one could print out a 1, 2, or a 3. So you may be able to loop over the 27 different combinations there, or maybe we'll be able to invent something more clever in order to check sort of, are we able to produce the desired sequence without having to go through those 27 combinations. But for now, let's see if we can just reach the milestone of looping over the different values of A, B, C, X, Y, and Z to produce our sequence with three print statements. All right, we're now ready to make some progress on our code here, and we just want to implement the loops over our variables. So we're going to start off with our loop over x. This is the same code as in the k equals 2 case. We're looping over all the values from 1 to n, and then if they don't divide n, we're going to continue on to the next value. Otherwise, we're going to check all values y between 0 and n divided by x. This so far is the exact same as the previous program. What changes here is now inside this loop over y, we're going to loop over the choices for A, B, and C. And remember that A has to be a factor of y. So we're going to loop over from 1 to y. And if A divides y, we will loop over all of the values B from 0 to y divided by A. And these are all the loops we need. We can calculate z and the value c using math formulas just like before. At this point, there's just 3 more steps until we're done the program. Our first step is we want to compute the sequence B produced by this program. So we've looped over the program, but now the question is sort of what sequence does that actually produce? Then we want to check, does that sequence equal A? Or alternatively, does that sequence reversed equal A? So this is just a handy trick for sort of handling both of these cases at the same time. Reversing this sequence can produce the sort of sequence produced by a program like this. So the question is just whether or not you put this for loop before or after the nested loop. So if we can complete these 3 steps, we are done. The good news is checking this sequence or producing this sequence B, we can do in a very similar way to the previous step. The only question is sort of what to assign to the print statements. So in the k equals 2 case, there weren't very many cases, so I could just check all the combinations of like assign 1 first and then assign 2, or assign 2 then assign 1. Unfortunately, in this case, there's a lot more combinations of ways to assign 1, 2, and 3. So what I'm going to do when I'm creating my output B is I'm just going to have a placeholder variable. So I'm going to have 0 represent the output of this first print statement. I'm going to have 1 represent the output of this second print statement. And I'm going to have 2 represent the output of this third print statement. And then the question that I want to answer is there an assignment of 0, 1, and 2 to the numbers 1, 2, 3 that produces the sequence A? And what that's going to look like here is I want to loop over the sequence B and check that 0 can be assigned to exactly one number. 1 can be assigned to exactly one number, and 2 can be assigned to exactly one number. So for example here, because it's always easier to sort of understand things with concrete examples, let's suppose our sequence B was 0, 0, 1, 2, 2, 1, 2, 2. And let's say the sequence A was the sequence 3, 3, 2, 2, 2, 2, 2, 2. The question is, can I assign the values 0, 1, and 2 to the values 3, 1, and or 1, 2, and 3, such that each number maps to exactly one number? And the answer here is yes. What I could do is I could assign 0 to 3. So all of the zeros in my B sequence are going to become 3s. All of the 1s should become 2s, and all of the 2s should remain as 2. So this 1 becomes a 2, 2, this 2 becomes a 2, becomes a 2, remains a 2, and so on. And we can see that there's an assignment from the values, which you can think of as variables, 0, 1, and 2, to make it equal to A. If, on the other hand, let's say A was a different sequence, let's say A was the sequence 2, 3, 1, 1, 2, 3, 1, 1. Now let's try to do the same thing. Well, the problem is here I need 0 to become both a 2 and a 3 simultaneously. So I need sometimes 0 to become 2, and I need sometimes 0 to become 3. That doesn't make any sense. So this would be a case where B is not equal to A. So what I want to do in this last step here is loop over the array B and make sure that each value in B corresponds to exactly one unique value in A. And in order to do that, I'm going to create the array matches. And this is just going to be the assigned value for each of the values 0, 1, and 2. So 0 will start at be assigned to -1. 1 will be assigned to -1, and 2 will be assigned to -1. As I'm looping over B, if I see 0 pointing to the value 2, I'm going to update this -1 and say that 0 now points to the value 2, so every 0 in the future will now need to become a 2. However, when I get to this second value, I can see that 0 has to also become a 3, so this is impossible. It can't be two different values, so I break. So as long as each number gets assigned exactly one value, I'm happy. If any number gets assigned more than one value, then I'm sad, and B cannot produce my sequence A. So let's loop over the values from 0 to n-1. This is just the indices in the arrays. And if matches BI is -1, this just means I have not seen this element before. So I'm seeing the value 0, 1, or 2 for the very first time. So I'm going to update it to its new value, which is just whatever value I'm currently seeing in array A. So for example, here, it's this step where I'd take 0 and update it from a -1 to a 2. Then, if this is not the case, so if it's already been assigned, then it better be equal to the value I'm currently seeing. So if it's been assigned a value and that value that it's been assigned is different than the value that I am currently looking at in the array A, then this is an impossibility result, right? So I can't have 0 assigned to two different values simultaneously. So I'm going to break out of the loop. I failed in my search. I know that B is not equal to the sequence A. So um, to check, have I sort of completed the search? I'm going to both want to ensure that I is equal to n minus 1. Have I gotten to did I get to the end of the loop? And then when I got there, was the condition of equality satisfied? So if both of these things are true, then I return yes. And there are other ways of doing this sort of final step here as well. You could store a Boolean variable that sort of stored your success state of like assume that you're successful, but then if you ever have to break out of the loop, switch success to false, and then you can just have a Boolean variable here determining whether or not you return yes or no. Um, and then for step 3, I'm just going to do the exact same thing, but I'm going to loop either over A in reverse or B in reverse. It doesn't matter as long as you do exactly one. So for step 3, I repeat the exact same block of code, except now I'm just looping over A backwards. And then if either of these two cases return yes, then I know it's possible to create my desired sequence because I literally constructed a program to produce that exact sequence. Now, this brute force is quite slow. It does pass all of the test cases, but you may pause and think, is there a faster way to solve this problem? And the answer to that is almost certainly yes. You could probably solve this problem in a linear amount of time with respect to n, but you'd have to do a lot of casework where you're sort of cleverly going from a sequence and then producing the desired program in some clever method, right? So you could sort of try to break the sequence and see how many times sort of like each subsequence repeats, and then build up the variables A, B, and C in some clever manner. However, in the context of USACO Bronze, if there is sort of a brute force method that works, I'm just going to do the brute force method that works. So a lot of students, they get caught up in problems like these, trying to find some idea that is too clever. And then they get these programs that are really difficult to implement. And even this program is a long program that is difficult to implement. But if you try to go down this route where you're looking for a much faster program, the length of your program will probably substantially increase. So this is a challenging problem, but you really want to sort of go back to that fundamental idea of see if you can brute force over it first, and then if brute force doesn't work, try more creative things. And in this problem, as long as you sort of are careful with how you generate your variables, you can brute force over all problems. And the fact that the variables in this problem are so small gives you a good confidence that brute force should be an effective strategy in this situation. So thank you guys for watching the videos. I hope you enjoyed this contest, and I'll see you in the next one. Bye bye, everyone.